Hello, this is Sean Mullery from Electronic Engineering and IT Sligo, and in this lesson we're going to look at the pulse width modulation facility that the 16F88 chip and many of the other PIC microcontrollers have. Now this is part of a module called the CCP module, which can also do two other things: capture and compare. I'm not going to be looking at those, I'm only looking at the pulse width modulation for the moment. The section that I've opened it here is section 9 of the document, and if you just search for PWM you'll find that eventually. And we can see here that between the capture, compare and PWM we obviously have the ability to choose one of these systems or one of these functions at any given time. So the main thing that we want to look at on this is just to determine what way we actually set it up that it will run the pulse width modulation. Okay, and on this we can see that in order to run the pulse width modulation, if we look down the bottom here of this particular CCP1 con, so it's the CCP and it's the as in the capture, compare and PWM module, and it's the control for that, so it's the control register for that. The bottom 4 bits from bit 3 down to bit 0, we can see that we have, to put it into PWM mode, we say 1 1 and then XX. XX means don't care, so it doesn't really matter what they are as long as we have a 1 and a 1 in bits 3 and bits 2 of this particular register here, CCP1CON. Okay, so you should take note of that in your notepad or whatever, in order to remember that you're going to have to do that in order to set the system up to run the pulse width modulation. Now from that point on we need to go further down here. So that's the capture mode, there is the compare mode, and then we have the pulse width modulation mode. Now pulse width modulation gives us the ability to have much more exact timing than we were managing to get by using our interrupt with a port pin. However, it is quite convoluted, quite complex on the PIC in order to get it working. So there's a little bit of getting used to actually using the system. So just to take a look through this section here, in pulse width modulation PWM mode, the CCP1 pin produces up to a 10-bit resolution PWM output. Now 10-bit resolution, that's gives us 1024 possibilities, but it says up to that, and that means that we won't always have that ability, but that's 2 to the power of 10, which is 1024. Okay, so that's the maximum resolution we could get, but we will only get that resolution at certain points. Now what that basically means is that that's how much we can split our individual period up into high time and low time. In other words, the smallest time high time we can have is 1/1024th of the full period. Okay, so it's the smallest high time we can have is 1/1024 times the period, so multiplied by the period. Okay, now that said, we won't always be able to get that quite that good a resolution. It depends on how long our period is compared to our frequency, the frequency of our clock signal that's coming in. But just to be aware that that is the maximum that we can have, and there's 10 bits involved. So since the CCP1 pin is multiplexed with the port B data latch, the TRIS-B, and it just says X, so it doesn't tell us which bit, must be cleared to make the CCP1 pin an output. Okay, now what this basically means is that whichever port pin that we're using it on, we need to make sure that that's set up as an output. This may give you the impression that we can use any of the port B's pins for a PWM output, when in actual fact we only have 2 options, and the 2 options are RB0 and RB3. Okay, so I'm trying to remember exactly where that was mentioned. I think it's further back here. We'll just see if we can find it. Yeah, CCP module's output inputs pin CP1 can be configured as RB0 or RB3. Okay, so we can see it there. It's just written there. Okay, RB0 to RB3, or sorry, RB0 or RB3, and this selection is set in bit 12 of CCPMX of the configuration word. Now that's the configuration bits that I've shown you before that we can set up. Now as it happens, I'm going to show it to you working on RB0 rather than RB3. You can run it on RB0, but we seem to be having issues running it on this version of the simulator. Whether it works on some of the other ones, I'm not entirely certain. And as to whether I'm just doing something wrong, I'm not sure. But it seems to me that whenever I set it up on the to run for RB3 in the configuration bits, it still runs on RB0. So I don't know if that's a simulator issue yet or something else that I haven't done correctly. But for the moment, we'll work it on RB0. Now, so we're in PWM mode here. Oh, apologies. Okay, so the PWM mode. Now, for a step-by-step procedure we can see here on how to set up the CCP module for PWM operation, we look at section 9.3.3 setup for the PWM operation. We look at that in one moment, but what I want to look at here firstly is the determining the PWM period and determining the PWM duty cycle. Okay, which we have both of them here. So I'll just get both of them up there at the moment. So PWM period we can see there is equal to PR2 plus 1 multiplied by 4 multiplied by T oscillator multiplied by the TMR2 prescale value. Okay. So what I'm going to do is I'm just going to pop over here to a little PowerPoint presentation where I can write this up for you and we can talk about how we're going to set this. Okay, so just to remind you of the formula, it's as follows: PWM period, and it's equal to the following: P or 2 plus 1 multiplied by 4 multiplied by T oscillator multiplied by the T or 2, say that's 2 TMR2 prescaler. Okay. Now, the thing is that normally what would happen is we would decide that we want a particular PWM period. So this seems to be that if I put in a value for PR2 and I put in a value for each of the other things on the right hand side here, I would find out what my PWM period is. But what happens if we decide we want a particular PWM period, which is what we would normally do, and then we need to figure out, well, what we're going to put in each of the other values of the things. Okay. Well, firstly, let's start by trying to get the important information that are the information that we do know all on one side of the equals and the information we don't know on the other side of the equals. Now, there are several things we don't know here. We don't know the value for PR2, we don't know the prescaler value, and we don't know the oscillator value. However, the most complicated of these is the PR2. We can just decide what the frequency of our oscillator is and work from there, so we can come up with a value for it. The prescaler, well, we only have 3 options. We've 1, 4, or 16 for this, so we can vary it as we go if we find trouble with doing it at a value of 1. So it's PR2 really is going to be the issue, and then we have PWM period, which we decide to start with what that's going to be, and then figure out what value to put in for PR2. It's a register that we're going to fill in order to give us the right thing. So what we're going to do is we're going to put the PR2 part, PR2 plus 1, on one side of the equals, and we can see that it's multiplied by everything else here, which means that if we take everything else and put it the other side of the equals, it'll be divided in. So that'll basically give us PWM period, and we're going to divide that by 4 times the TOSC by TMR2 prescaler. Okay, So let's imagine that I've decided that I want the period of my PWM signal, that's in the full, including the high and the low part, to be 100 microseconds. Okay, so I'm going to put in 100 microseconds for that. Let's say that I'm assuming that I've got a 4 megahertz crystal. Okay, now 4 megahertz crystal, if we want to find out the T oscillator, in other words, the period of that oscillator, it's 1 over 4 million. Fit all those zeros in there. Okay, so if you check that on your calculator, you should find that it comes in something like 0.0000025, okay, or 25 by 10 to the minus 8, or 0.25 by 10 to the minus 6. Now the important point here is that this is multiplied by 4, so basically those 425s are going to come out to become a 1 there at that. Okay, so the 4 multiplied by T oscillator should give us a 1, which is effectively 1 microsecond. Okay, and we're going to multiply that by the prescaler value. Now, if you were looking at PR2, the value of PR2, you'll have found that it was an 8-bit register, and so what we can do is we can fit any number between 0 and 255 into that. So for the moment, we'll just assume that we're going to put the prescaler at a value of 1, so that's basically 100 over 1 multiplied by 1, which is just 100. Okay, so PR2 plus 1 equals 100. Therefore, PR2 must equal 99. Okay, so that's the value that we're going to do to get ourselves a duty cycle. Sorry, that should say PR2, not RR2. So PR2 is going to be assigned 99, and that will give us a duty cycle of 100. Okay, now to look back at the, so I'll just escape there for a second. And I'll go back to the document. We can see that down here we have the equation for the PWM duty cycle, and it's we're given some values for registers: CCPR1L, CCP1CON 5 and 4. Now basically what they are is the CCPR1L, that's this, we can see it written here, CCPR1L. It's an 8-bit register, okay, and if we add on the 2 bits 5 and 4 from CCP1CON, we get 10 bits altogether. That's what we mentioned earlier when we said we had 2 to the power of 10 here that gives us 1024. Now, as it happens, the 8 bits of CCPR1L, they're the 8 most significant bits of that 10 bits, and then the 2 least significant bits are the 2 down below. Now, what we want to do is we want to multiply that by T oscillator and multiply it by the TMR2 prescale value. Okay, so we'll go back to our PowerPoint presentation here, and I'll write these in. So we've got the, this is for the PWM duty cycle, PWM duty cycle. And what we're going to do is we're going to take the 10-bit number that we're going to put into those CCP registers, which we don't know what they are. So I'm just going to call that X 10-bit here. Okay. Actually, maybe I'll just call it 10-bit. Because X might give us the impression there's a multiply. Okay, now that's multiplied by T oscillator, and it's multiplied by the TMR2 prescaler. Now, previously we set the prescaler to 1, so that gets rid of that bit. That just becomes a 1. It's multiplied by T oscillator, which is 0.0000025. And then we've got our 10-bit number here. Okay, now, and that's going to be multiplied by that. Now, you notice we don't have a 4 multiplied by here, and it would be simpler if we did, because that would basically change that into being a it would change this into being a 1 on the bottom here, right? Now, you remember when I did this, we ended up with 0.000001. And you might say, well, why didn't I put that number in? Why did I put a 1 in instead? Well, the reason was I had 100 microseconds on the top. I had given this in microseconds on the bottom, so the two would cancel each other out. I should have kind of said that at the time, but that's effectively what I'm doing. Now, the same thing can happen here. We want to give the duty cycle, we want to give, in other words, the number of microseconds that it's going to spend at its positive value. We want to give that in microseconds for the moment. So it'd be handier if I took 2 of the bits off the 10 bits and used them to figure out what my value would be in microseconds. If I want to go below a microsecond, that's fine, I can do that. But the thing is that, as we know, this is made up of 8 bits and 2 bits. And 2 bits, if we think about it, would be a 0. If we had a 0 and a 0 and then a 1 over here, that would effectively account to a multiplying by 4. Because if you remember, if we shift by 1 bit, we're multiplying by 2. If we shift by 2 bits, we're multiplying by 4. So in effect, if I just looked at the 8 bits, okay, so if I just have my 8 bits here, 8-bit value, and I multiply that by 0.000001, in other words 1 microsecond, then that will give me the PWM duty cycle. Okay. Now this 8-bit number is the number that I don't know, so what I'm going to do is I'm going to say the 8-bit number, the 8-bit number is equal to the PWM cycle, PWM duty, divided by 0.000001. Now remember, we normally give the duty cycle in terms of microseconds as well. So imagine that I wanted to be on for 30 microseconds, for example. That would be 0.000030. And therefore that would divide in 30 times. So my 8-bit number that I'd be looking for would be 30. And I'd put that number into it. Okay, so just remember those details. That's how we do it. We will also have to make sure that those 2 bits on their own, which we mentioned earlier, so I'm just going to go back and show them to you, because when you first see them, it doesn't make a huge amount of sense what we want to do with them. So if you remember here, CCP R1L, that's going to be the 8-bit number that we have there. So if we want it for 30 microseconds, that's that number that's going to go in there. CCP1CON, that's those 2 bits, 5 and 4. You're going to have to set those to 0 if we want to do the 30 that we've just done, which means that they will both be set to 0. So it's effectively like multiplying the oscillator frequency by 4. In order to get us closer to the value. Okay, I'm going to leave the recording at that, just so that you have a special recording just on how to do the calculations of the PWM, and in the next lesson I'm going to actually use these numbers in my actual code so that you see the PWM signal coming out.